Hello viewers. Now in this tutorial, we'll be learning how to solve this magnetic field question. This is another question on how to use the right hand rule, to determine the direction of the magnetic force on a charge moving through a magnetic field. Now the question reads, a proton moves with a velocity of, now we have the speed vector, which is 2I minus 4j plus k. The unit is the meters per second in a region in the magnetic field. Now we have B, which is the magnetic field vector, and this is given to be I plus 2j minus 3k, and the unit of magnetic field vector is the word Tesla. What is the magnitude of the magnetic force this charge can experience? You know, IJK, I represent the unit vector in the x direction, and then the j represent the unit vector in the what? Y direction. Yk represent the unit vector in the what? In the z direction. So now, to be able to calculate the magnetic force a charge, moving in the region of magnetic field can experience. So, like I said, we're going to apply the right hand rule. Now, there's this equation which we are all familiar with, and that's the equation connecting the magnetic force on the moving charge with the magnetic field, the magnetic field intensity. So it is important for us to note, that the force, the force on a charge, is proportional to the vector product. Is proportional to the vector product. Is proportional to the vector product of the speed of the moving charge, which is the vector speed. So, or the speed vector, the speed of the moving charge and the magnetic field. So the equation for this, that will be the magnetic force will be equals to Q. Now remember, Q is a scalar quantity. That is why you will see that when I wrote V and B, I have to indicate a directed line segment over it. So over the two quantities. That is because both are vector quantities. So we have V, then multiply by that's V multiplied by B. This is the cross product of the speed, vector and the magnetic field vector. Now, in this case, we use the right hand rule, to determine the direction of the magnetic force of the vector product of the speed vector and the magnetic field vector. Now, in this case, what is important here is that the right hand rule, how does it apply to this? In this case, when we have two vectors, that's cross product or vector product of two vectors. Now, this is because there are two versions of right hand rule. We have one of the version, I used that in my previous video to explain why we have the direction of force, the direction of magnetic field, which move through the smallest angle, and then also the direction of what? Velocity. I said for the first one, the one I explained in the previous video, I said that when we point the fingers of the right hand, in the direction of velocity, then the thumb finger, we point in the direction of the magnetic force on a positively charged particle. Then the curled finger will point in the direction of the magnetic field. So that's one version, But when it comes to vector speed and magnetic field vector, so in this case, it will be we're going to use a different rule. We have to choose one, pick one out of, because in this, now, because we have cross product of V and B, these two are vectors. So it means that we have the velocity and the magnetic field intensity to be given in in the unit vector notation. We are given in the unit vector notation. So what we need to do here, because we are given V, to be 2I minus 4j plus k, okay, and the unit is the what? Meters per second. Then also we are given B, which is what? I plus 2J minus 3K, okay, which is given to be what? The unit is the what? Tesla. Now, what we need to do in this case is now to write the vector product of B, that is the cross product of B and V, that's V and B. The right hand rule we are going to apply in this case is when we hold, as in when we hold our right hand, our open right hand like this. That is, hold your right hand, that is, hold your open right hand like this. You know, this is the right hand. So hold your open right hand with the thumb finger pointing in the direction. Okay, it's going to be like this, pointing in the direction of the first named vector quantity. That is, the thumb finger will point in the direction of A, okay, and then the second, that's the fingers of the right hand will now point in the direction of the second named vector quantity, which will be what? B. Then the third, that is this third vector, which represents C, okay, will now represent the resultant vector, okay, which will be what? Which will be directed out of the what? The palm of the what? Of the fingers. That is, like I said, hold your open right hand, okay, with the thumb finger pointing in the direction of the first name vector quantity, which is A. So we have cross product of vector A and B, okay, and I said the fingers of the right hand, these four fingers, okay, will then point in the direction of the what? The second named vector, okay. Now the resultant vector, which is the third vector, that is cross product of A and B, will be equals to what? C. So this third vector is the resultant vector, which will now be directed out of the what? Of the palm of the fingers of the right hand, and that is the resultant vector. So we're going to use, so in this case, we're going to write this in matrix form, because what we have here, we know that the magnitude of charge is 1.602 times 10 raised to the power of minus 19 coulombs. So this will be, the magnetic force will be equals to, so we have 1.602 times 10 raised to the power of negative 19. Then we now have, then multiply by V, which is 2I minus 4J plus K, okay, then multiply by, that is cross product, okay, I use the multiplication sign, that's cross product or vector product. So that will be the value, then B, we have, that will be I plus 2J minus 3K, okay. So this cross product, okay, is why we have to transform this into what? Matrix form, okay. This will be transformed into what? Matrix form. So we need to write this in matrix form. Or there's also a formula, okay, we can use a formula, you know, to, there's also a formula, a standard formula we can use, okay, to calculate this, the value of F. Okay, so now to put this in matrix form, now in matrix form, we know that because we have the what? The cross product of vector, that's the speed vector and the what? The magnetic field vector. Because we are giving the speed vector and the magnetic field vector, the cross product. So what we need to do is to, like I said, we write it in matrix form, this product. So we know that this will be V, cross product of V and B, okay, that will be IJK, okay, okay. So now we're going to have the determinant of, so we're going to put this value, so we have 2 minus 4, okay, then 1, then this will be 1, 2, then minus 3, okay. So what we need to do now is, so we have the determinant, so we need to expand the determinant. So to expand the determinant, we have the cross product of the speed vector and the what? The magnetic field vector to be, so this will be, we know that I multiply by, now we're going to have multiply by negative 3 times 4, that is, let me do it this way, negative 4 times negative 3, then minus 2 times 1, okay, this is mathematics, okay, matrices, then minus j, okay, open parentheses. So we have negative 3 times 2, that is 2 times negative 3, okay, 2 times negative 3, 2 multiplied by negative 3 minus, okay, so 1 times 1, okay, we have 1 times 1, so 1 times 1, okay, so we have 1 times 1, so then plus k, that is the unit vector k in the what, z direction. So we open parentheses, so this will be 2 times 2 minus negative 4 times 1. Okay, so the cross product of v and b. So let's obtain the vector. Okay, you know, this will be equals to a single vector, which will represent the resultant vector that will be directed out of the what, of the palm of the fingers of the right hand. Remember I said when we hold, you know, when we hold your right open, that is, hold your open right hand, okay, like this. Now the thumb finger, okay, with the thumb finger pointing in the direction of the first named vector, okay, the first named vector, the first named vector. So this is the first named vector. Then this is the second named vector, which is B. Now the third named vector is C. So there will be some angle between A and B, okay? So that's that. So the third vector is the resultant vector, which will be directed out of the palms of the fingers of the right hand. So in this case, this will be 12, okay, minus 2. I, okay, negative, this will be minus 6 minus 1, then j, then plus, this will be 4 plus 4, then k. All right, so this will be the cross product of the speed vector and the what, that's the two vectors will be, this will be 10i, this will be minus 7, then this become plus 7j, then plus 8k. So this is the cross product of the two vector field we are given, that is the magnetic field vector and the speed vector. So now remember what we have here. So we've been able to what, to determine the cross product of these two vectors. So we are going to use it to multiply the force. Okay, so we can now we can then say that recall, we have the what, the magnetic force to be, you know, 1.602 times 10 raised to the power of negative 19. Okay, so that will now be multiplied by, remember we just find out the what, the cross product of these two vectors, okay, and that is what we have here as 10i plus 7j plus 8k. Okay, so now, so what we are doing here is to find the vector force. Okay, you know, I said, now of course we know that A, B, C, when it comes to using right hand rule to determine the direction of the cross product of two vectors, we know that A, B, C represent the first named vector quantity. So is this the force or the velocity or the what, the magnetic field? I'm sure we know that the B stands for the magnetic field intensity, because I explained this in my previous video. Okay, now that is when, and that's why I said there are two versions for the right hand rule, not the right hand grip rule. Okay, there are two versions. So one of them, I use it in my previous video to solve the question, a question that has to do with the word, the right hand rule. When we have to hold, when we have to point the fingers of the right hand, okay, we point the fingers of the right hand in the direction of velocity, okay, but because we are giving vectors in this case, this is a vector, this is a vector, so that's why we have to use the second or the first version of it. Okay, so this is the other one is the second version. Okay, so it points in the direction of what, velocity. The thumb finger point in the direction of force, and that will be A. This will be the direction of what, velocity. Okay, yeah. Then down the magnetic field, and this will be in the direction of the what, velocity. So it's the same thing, but because the two vectors are are given in what? In unit vector notation. So that is why in this case, this equation, that is the vector force, that is the magnetic field, the magnetic force, which is equals to the product of Q and the cross product of vector V and what? Vector B. Okay, that is the definition for what we call the magnetic force. That is when we are when it comes to how to determine the direction of the cross product of two vectors. So we have this. So now what we need to do here is, so to calculate F, so this will be 1.602 times 10 then I plus 1.602, okay, times 7J plus 1.602, okay, times 8, and that will be K. So we close the parentheses. Okay, so now then everything will be multiplied by this 10 raised to the power of negative 19. Don't forget that the unit will be what? Newton, because now we have 1 meters per second multiplied by Tesla. Okay, then multiply by, that is 1 coulomb, then meters per second times Tesla will be equals to 1 Newton. Okay, will be equals to 1 Newton. So that's why the unit will be what? Newton. There's nothing to do again to show why the unit of force in this case will be what? Newton. So 1 coulomb meter per second square multiplied by Tesla, which is the unit of magnetic field vector, will be equals to 1 Newton. Okay, so now, so F will be, so in this case, this will be 16.0, okay, I plus, now when this is multiplied by 7, 1.602 multiplied by 7, okay, that will be 11.214. So we have 11.214, that will be J. Okay, then also 1.602 multiplied by 8, okay, that will be 12.816, that's K, okay, which is the unit vector in the Z direction. So now remember, we want to find out the magnitude of the magnetic force, okay, this charge can experience. The charge is what? Q, which is 1.602 times 10 raised to the power of minus 19 coulomb. So what we do is, we're going to what? So to find the magnitude, okay, the magnitude of F denoted, okay, denoted by, so this is the magnitude, this is what it is, we can denote it by, so this magnitude, okay, will be equals to, so we can write the square root of, so remember in this case we are going to use dot product. When we square I, that will be 1. When we square J, that will be 1. When we square K, that will be 1. So but let's get the square of, so this will be 16.02 I square plus 11.214 J square, okay, plus 12.816, okay, 816 square, K square, okay, K square. All right, so let's get the values. So 16.02 square plus 214 square plus 12.816 square. Altogether, we have the magnitude of F. Remember, the magnitude of F, that will now be 546.644. Now, don't forget that we're going to multiply this by what? 10 raised to the power of negative 19. This guy here. So, and the unit remains Newton. The unit is in Newton. So, I'm still going to multiply this by minus 19. So, the unit is Newton. Okay, now, so So what is now the square root of 546.644? That will be 23.38. So we can now have the what? The force. The magnetic force will be equals to 23.38 times 10 raised to the power of minus 19 Newton. And let me write it here. So we have the magnetic force to be equals to 2.338 times 10 raised to the power of, that will be 10 raised to the power of 1, then multiply by 10 raised to the power of minus 19. So that the magnetic force is 2.338 times 10 raised to the power of negative 18 Newton. So this is the force, the magnitude of the magnetic force on proton, which is a positively charged particle moving through a magnetic field, okay, with a magnetic field whose intensity is what we are given here, okay, with a velocity 2I minus 4J plus K, okay. So this is the, and note, like I said, I square, okay, is equals to 1, okay. J square is also equals to 1, and then K square is also equals to 1. So which means when we take the square of 16.02 I square, because I square is 1, so we can only get the square of 16.02, okay. So, and also the same thing applies to 11.214 J square, okay. So that means the J square will be what? 1. The same thing we have here, 12.816 K square, okay. So the force, so the magnetic force is 2.338 times 10 raised to the power of minus 18 Newton. The noblest pleasure is the joy of understanding. Bye-bye.